Okay, welcome to lecture 20. I think we have 6 more lectures left after this in digital design and computer architecture. We're going to cover another concept that has had a lot of impact on modern computers. I should say that has enabled some general purpose supercomputers to be in our pockets today. And these are called GPUs, graphics processing units. And we're going to cover the details of graphics processing units in lecture 21. But today we're going to build the foundations for how they operate essentially in a single instruction multiple data manner. But before I get to those foundations, let me make an announcement about lab reports. Essentially, you can submit your lab reports late in Moodle. This will be open until June 20th, as you can see over here. And there are no extensions after that. And you can submit any past lab report that you have not submitted before its deadline, but you're not allowed to submit anything that you have already submitted via other assignments. I'd like to give this opportunity for you to learn if you have not done it already. But of course, these are late reports, so we will grade them, but late submission has a penalty of 1 point, meaning you get 3 points per lab in the course, right? In the entire course points. So the highest possible score per late lab will be 2 points. Which is still a pretty good deal, I think. It's 2 out of 3 in the end. Another announcement, today we're going to hopefully talk about Amdahl's law a little bit, because the machines that we're going to look at will have serial bottlenecks. And I wanted to assign another paper, which is another 2-page paper only, that was written in 1967, that essentially introduces Amdahl's law. How many people have learned about Amdahl's law in past courses or in some other way? I don't know if I see any feedback. Okay, somehow I messed up in my slides. Sorry about that. Looks like I get this semester parallel programming. Okay, that's good. Yeah. Now you will get to read about it also. I'm going to briefly discuss it also during the course of this lecture, but hopefully this will be fun. And by doing this, you will have read both Moore's paper and Amdahl's paper, which have shaped computing in essentially all aspects of computing, actually, for more than 5 decades, as you can see over here. Okay, and please, this is 1% extra credit. Due date is June 15th, as you can see. And please try to follow the suggestions that we provide on how to review papers. And there are examples of it. There's a video of it that describes how we suggest to review papers. And this could be useful for you beyond this assignment, of course. Okay, and this is the paper that you're going to look at, basically. And we're going to talk about it. Okay, basically, we're almost done with this slide. Everything in the slides, we've dedicated a lot of lectures to essentially improving the performance of computer microarchitectures that we're designing. And we've been looking at other execution paradigms in the last several lectures, actually. And we've covered essentially all these paradigms that are in gray, which is great. We've covered in the last lecture VLIW, systolic arrays, difficult to access and execute, all our concepts that have had a lot of impact in the design of systems. Today, we're going to cover SIMD processing, and especially focus on vector processors today, but we're going to also talk about array processors. And then next week, we're going to talk about GPUs, which essentially combine the concepts of vector and array processors with a different programming model than the programming model that we're going to see for SIMD or traditional SIMD machines today. So it's going to be a lot of fun. As I said, GPUs are everywhere today. That shows that the concept of SIMD has been very, very successful over decades, as you can see, and but with a better programming model potentially, right? Okay, so these are the readings for this week and also next week. Actually, I'm not sure if we will get to the MMX technology, which is essential SIMD concepts applied in a von Neumann architecture like x86. But this is the required reading for the GPUs. Unfortunately, I don't have great readings for the SIMD part, but maybe in the future we will actually have something that's written by us. Okay, so basically we're going to talk about exploiting data parallelism, and that leads us to SIMD processors, single instruction multiple data processors, and GPUs overall. So I also think about this as exploiting regular parallelism. Essentially, you have some regular parallelism. You have one operation that needs to be done on many pieces of different data elements. And it's regular in that sense, basically. You have single operation that you need to do on many data elements. or pairs of data elements, let's say. This will become more clear soon. So it's very different from what we have seen so far, in a sense. It's different from systolic computation also, as we will see soon. Okay, so to understand this a little bit better, this is another work that had a lot of influence in the development of computing systems. This was written by Mike Flynn in 1966, as you can see. Here, he develops a taxonomy of computing systems, very high-speed computing systems, as he puts it. And essentially, he looks at two dimensions. One is how many instruction streams you have. And the other dimension is how many pieces of data, let's say pairs of data, does an instruction stream or instruction in the instruction stream operate on. So far, we've been looking at single instruction operating on single data elements or a single pair of data elements. If you have an add instruction operating on two registers, for example, writing the result back to some other register, you're operating on two data elements, producing a result and writing it back, right? Essentially, you have a single instruction operating off single piece of data. Whenever I say piece of data, think of if the instruction has two operands, it's also pairs of data, right? If the instruction has three operands, three. But you don't repeat the instruction on multiple sets of operands, basically. So in that sense, SISD is very simple. Single instruction works on single data. You can also have SIMD, which we're going to cover today. Basically, the main difference will be you have a single instruction that does the same thing, exactly the same thing, except on multiple data elements. Multiple can be specified by what we will call vector length. It could be 4 elements, 4 pairs of elements. So when you do an add, you specify the add operation, and then we will also specify essentially vectors and how many elements, how many pairs of elements the add will do the addition on. It could be 1 million pairs of elements if you're adding 2 1 million element vectors, for example. So this could be very powerful, as you can see, because single instruction specifies many operations now without actually encoding the instruction many times. Okay, we're going to see examples of this, array processor and vector processor, and we're going to look at that. There are also 2 other examples of this taxonomy. Clearly, you have instructions on the x-axis in one dimension and data in another dimension, and data can be, both of them can be single or multiple. As a result, you have 4 possible different types of computers. MSD is an interesting one. Multiple instructions operate on a single data element. This is an interesting one because the closest form is something that we have seen earlier, actually, which is a systolic array processor. Essentially, multiple instructions actually is a stretch because systolic arrays normally don't necessarily have instructions, they have operations. But if you think about generalizing a systolic array, like we discussed at the end of the last lecture, as a streaming processor, for example, you're streaming in data and you get one data element, an instruction, an operation transforms into another data element, and then passes it on to another instruction, right? Another operation. So you keep doing this in this one-dimensional array of cells, let's say systolic cells. You could also make it 2-dimensional, right? So MSD is actually best exemplified by a systolic array processor. You load one data element and you transform it into something else as you pass it between different instructions, right? And streaming processor is another example, as we discussed in the last lecture. And finally, we have MIMD, which is essentially multiprocessors or multiple threads. Here you have multiple instructions concurrently operating on multiple data elements. Essentially, you have multiple instruction streams here. So you have a multiprocessor or a multi-threaded processor. If you're doing parallel programming, which you are, essentially, whenever you program a multiprocessor, you're executing multiple different instructions on multiple data elements. So wouldn't MIMD be multiple SISD? That's one way of designing MIMD, yes. MIMD can be multiple SISD also, but essentially, yes, with this definition that I provided you over here, you can think of it that way. But there could be other forms of it also. So this is a more general definition. We may actually see some other processors that look different from potentially SISD. Internally, MIMD can be SIMD also, right? Internal. So you may actually have MIMD processors consisting of multiple threads, each of them consisting of SIMD instructions, right? You don't do it today, potentially, but that's possible. Or you may have MIMD, multiple instruction streams, where each instruction stream does MSD. So you can actually combine these concepts in different ways. That's why I think it's better not to limit us to multiple SISD. But existing multiprocessors, symmetric multiprocessors, for example, yes, they are multiple SISDs. Like if you take a multi-core machine, there are multiple SISDs today. So SISD is interesting. So one thing I should also mention is VLIW is also SISD, right? Even though you have multiple instructions at the same time packed together, each instruction within a packed bundle really operates on one single data element. So in that sense, VLIW is SISD. But again, you can stretch it perhaps. It's really, you're really operating on multiple instructions at a time, but they're not independent of each other. Okay, here things may be blurred a little bit. As you can see, VLIW was developed more than 15 years after Mike Flynn invented this taxonomy. So, okay. So this is the paper. If you're interested, I would recommend reading it. It's actually a nice read. It's a little bit old language, but you can see that abstract directly defines what it's going to talk about. And this is the picture of a MSD example. Basically, you have multiple instruction streams, and you have single data. So this kind of looks like a systolic array, as you can see, right? You have a source data stream, and you're streaming it into execution units. And execution units may be executing different instruction streams, as you can see. And one execution unit operates on the data and transforms it into a derived data stream, as Flynn calls it. And you keep doing that. So this part is very much like a systolic array, as you can see, but it's a more generalized systolic array because you can do arbitrary programs potentially on these execution units, right? So it's more like a streaming processor, like we discussed last time, or pipeline parallel execution, as we discussed also. SIMD example looks like this from Flynn. Basically, you have a single instruction unit, and that single instruction unit supplies one single instruction to many execution units, as you can see, which fetch from different operands. Essentially, here in this example, you have 4 execution units operating on, performing the same instruction on different data elements. And that's essentially what we're going to see. This is similar to an array processor, as we will see. Okay, so we're going to cover SIMD in this lecture, and we're going to go a lot into it, so hopefully it'll be a lot of fun. But before covering SIMD, let's talk about data parallelism. Essentially, what SIMD exploits is data parallelism. You do the same operation on different pieces of data, and concurrency arises from this fact. And that's why it's called SIMD, single instruction, multiple data. An example is dot product of 2 vectors, right? Or even addition of 2 vectors. We will later see averaging, element-wise averaging of 2 vectors. Whenever you do operations on multiple vectors, you actually can create this sort of parallelism very easily. So if you have huge matrices, for example, 1 million by 1 million, clearly you have a lot of parallelism because each, if you're doing matrix multiplication on those matrices, you're basically multiplying huge vectors, right? And essentially, a single instruction is specifying a lot of the same operations to be done on different pieces of data. So contrast this with data flow. So in data flow, as we have seen in both the data flow at the ISA level paradigm, as well as out of order execution, concurrency arises from executing different operations in parallel in a data-driven manner. So this is very, very irregular, right? Data flow was very irregular. SIMD is, in contrast, very regular because same instruction is applied to many, many data elements. In data flow, you can exploit similar parallelism, clearly. Data flow can identify which instructions operate on different data, the same instruction. But again, you're not bundling that action, that operation into a single instruction. So that's we will see that inefficiency in data flow. So if you're doing the same operation on millions of data elements, SIMD is extremely efficient. Clearly, you can encode the same thing as a million instructions, right? As we can do in a SISD machine, single instruction, single data machine, but that's not very efficient, as we will see. Also contrast this with thread or control level parallelism. This is like a MIMD processor, multiprocessor. You program with multiple threads, right? And concurrency arises from executing different threads of control in parallel. And these threads can be doing completely different things, right? They don't have to be doing exactly the same thing, clearly. We will see what happens if these threads are doing exactly the same thing when we talk about GPUs, actually. GPUs are programmed that way. You basically take threads that are doing exactly the same thing and combine them into SIMD instructions internally. Don't worry about that right now, but I'm foreshadowing what will happen in a GPU later on. But in a MIMD processor, in a multiprocessor or a multi-core processor today, thread parallelism is very different from data parallelism, right? Threads are really different control structures that are executing concurrently. So essentially, SIMD exploits operation level parallelism on different data. Same operations concurrently applied to different pieces of data. It's really a form of instruction level parallelism or operation level parallelism, whatever you would like to call it. But instruction happens to be the same across the data, basically. So you're adding two vectors, vectors A and B, element-wise addition. Basically, you're doing the addition on every single element of those vectors. If the vectors have 1 million elements, you're going through vector elements 0, 1, 2, 3, 4, 5, 6, all the way to 1 million minus 1, and doing that addition 1 million times. Okay, so it's really a form of instruction level parallelism also. So many people actually confuse this. SIMD really is exploiting some sort of instruction level parallelism where instruction happens to be the same across different elements of data. Okay, so I already said this, single instruction operates on multiple data elements, but there are two major forms of it, and I'm going to give you the purist's distinction. You could do this in time across consecutive cycles. Basically, you can operate on different elements of a vector across consecutive cycles, right? You take vector 0, 0th element, vector 1's 0th element, add them in one cycle. And then you take the second element from each vector and add them in the next cycle, in the next cycle, in the next cycle. That way, the addition takes 1 million cycles, but you're still exercising this sort of concurrency, especially if you're pipelining the addition units, right? Execution units. So this is time. There's also space. You can actually add all of those vectors concurrently because all of those vector elements concurrently because there are no dependencies between them, right? You could do the addition of every single ith element concurrently. So you may need 1 million units, of course, to be able to do that. So basically, this time-space duality is important because clearly space, if you do this in space, you can be much higher performance, but then you need a lot of execution units also. Okay, so basically, we'll still have multiple processing elements, execution units, but time and space, how we exploit the single instruction multiple data phenomenon in time or space will determine how much cost we will have, how many elements we need. So this duality is expressed as the array versus vector processors, basically. In an array processor, instruction operates on multiple data elements at the same time, using different spaces, basically. Processing element. Space is called a processing element in this case. We will see an example of this. Basically, if you want to operate on 1 million element vectors, maybe you have 1 million processing elements. Okay, and then you can do the same operation at the same time on all elements. Vector processor is more frugal, meaning you need less hardware. Instruction, same instruction, operates on multiple data elements in consecutive time steps using the same space. Now you're very frugal because you're using the same processing element, but you're using it for different data elements to execute the same instruction over time. So I think this is best exemplified with an example. But before I go into the example, I should also introduce the concept of vector registers because it's going to be important. I'm going to give you an example that distinguishes vector and array processors soon. But let's take a look at how we do it first. Basically, we're going to operate on vector data registers, which store essentially vectors. Each register stores a vector. Contrast this with a single scalar value. Remember, in MIPS, R0 stores 32-bit value. Okay, now we're going to add one more dimension to it. Instead of having one 32-bit value, we're going to say we're going to be able to store n 32-bit values if m happens to be 32. Okay, so n could be 64, for example. We're going to see an example where n could be 64. In hardware, you have 64 elements that could be stored in a single vector register, right? This way, you can have vector 0 64 elements stored here in one register, vector 1's 64 elements stored here in another register, and every cycle, you can get one element and feed it, one element from each, and feed it to a processing element, which is essentially an adder, for example, if you're doing the addition like we discussed. And then the result at the end of the cycle, or at the end of some number of cycles, if this is pipelined, result will go into some other register, and you put it into vector 2 0th element, for example. Basically, you will have instructions, one instruction specifying operations on a vector length. Vector length could be up to n in this particular case because the hardware can support n m-bit values in a single vector register. And the instruction, basically, we will set the vector length. And after we set the vector length, when we specify a vector add, for example, vector add operation, the vector add operation will basically do the addition on that vector length number of elements. Assume that the vector length is n. We say vector add vector 0, vector register 0, and vector register 1, store the result into vector register 2. What the hardware will do is, every single cycle in a vector processor, take the first element from V0, which is V00, put it into the processing element input, take the first element from V10, put it into the processing element input, and start the first addition. Once that addition is done, the data gets stored into V20 element. In the next cycle, you start the addition on the elements 1 from each vector. In the next cycle, you do the addition from elements 2 from each vector, ... until you get to n-1, which is 63 in this case. Okay, so it's a beautiful concept, as you can see. You're basically pipelining the operands from a long register, a vector register, into a processing element by feeding one data element every cycle. Okay, and I mentioned this in the example of a vector processor. In vector processor starts an operation every cycle, but we will see now the distinction between array processors and vector processors. Okay, now let's take a look at that. So now that I've explained you the difference between what a vector register is, this simple code, what it does is it loads 4 elements from memory, location A, consecutive locations, let's say for now, into a vector register, essentially 4 elements, let's say. I am going to simplify it because I want to show you a timeline over here. And then the next operation is a vector addition, which increments those 4 elements by 1. The next operation is a multiply operation, which multiplies the resulting incremented value by 2. And the next operation is a store operation, which stores essentially the output of this multiply, 4 elements, and puts it into the location where vector A was fetched. Basically, this code updates 4 elements of a vector by adding 1 to each element, multiplying the result by 2, and storing it back to its location. So it's a very simple code, as you can see, and you can see it in real programs. Many scientific programs do things like this, for example. So let's take a look at how these instructions get executed on array processors versus vector processors. As I said, array processor, you have processing elements, and you do all 4 operations concurrently. Okay, so you load all 4 elements of the vector at the same time and place it into a vector register. Sounds good, right? Now your vector register needs to be multi-ported, as you can see, 4 ports. And you need to have 4 load units, clearly, right? Which is going to be different from the vector processor over here. Okay, so in one cycle, you finish 4 operations, 4 loads. Now you have all the vector elements in the vector register. You can start the add. We're assuming that this is taking 1 cycle, of course, right? Now you start the add. What add does is it increments everything by 1. So this processing element will operate on the first element of the vector, incremented by 1. This one will operate on the second element. This one will operate on the third element and fourth element. And you can do all those increments by 1, assuming the instruction takes 1 cycle. We're going to later look at longer cycles, but this is a demonstration. Multiply later takes the result of the add for each element and multiplies it by 2. Okay, so you can do all of those 4 multiplies at the same time. And store takes the result of the multiply and stores it into memory locations consecutively, as you can see. So basically, in an array processor, what we did was we could execute all of these in 4 cycles, assuming each operation takes 4 cycles, because we have 4 processing elements that can do any operation. So the cost is really processing elements, as you can see. You can see that this processing element should be capable of doing all of the possible operations, as is this processing element, as is this processing element, as is this processing element. And we just looked at a vector length of 4 right now. If your vector length becomes 64, you need to have 64 of these processing elements. Okay, let's take a look at how this gets executed in a vector processor. Remember, in vector processor, you start 1 operation per cycle. So we start the load of 0 in the first cycle. In the next cycle, we can start the add of 0 in the addition unit. And we can start the load of the first element of the vector. Okay. In the next cycle, we can start the load of the second element of the vector, while the addition can actually continue, get the result from this first load and add the first element of the vector. And multiplication units can be operating on the 0th element of the vector, as you can see. And in the next cycle, if you think this is our pipeline is full now, if you will, basically we start the load of the third element of the vector, while the addition is working on the second element of the vector, while the multiplication is working on the first element, and store is working on the 0th element. We're storing now the 0th element, as you can see over here. And so on, basically. Now, the adder is working on the third element, multiply second element, store first element, and so on, essentially. So to be able to execute this code, clearly we took longer right now, because we didn't have all processing elements capable of doing everything. We had just one load unit, and we started the different element loads in consecutive cycles. We had just one add unit. We started the different element adds in consecutive cycles after the values available. We have one multiply unit. We started the multiply of different elements in consecutive cycles after the value is available, input value. Clearly, you can see the dependencies over here, right? All of these instructions are dependent on each other. And then store the same story. But the distinction between array and vector processor is clear. In an array processor, you execute the same operation at the same time in these processing elements. Whereas in a vector processor, we execute different operations at the same time. So this is the time difference. Let's take a look at the space difference also. Space is, remember, the execution units or processing elements. Basically, if you look at a given space or given processing element, an array processor is executing different operations in the same space. So it needs to be much more powerful in a processing element. Whereas a vector processor is executing the same operation in the same space, which means that it doesn't need to be as powerful. You can have load, add, multiply, store, one of each, as opposed to 4 of all, right? So basically, that's the basic distinction between a vector and an array processor. Keep this in mind. Existing systems are actually a combination of both. Basically, existing systems will be a combination of both vector and array, and we will cover this at the end of this lecture and later when we discuss GPUs. Okay, so are vector registers a distinct part of the hardware, or are they general purpose registers? So basically, these could be general purpose registers. Sure, in a vector processor, in a SIMD processor, it could be a general purpose register. You could have both types of registers, as we will see also, because this is very good at executing single instruction, multiple data operations. But you could also have another part of your processor that has more MIPS-like registers or scalar registers, right? So basically, there's no difference. These are actually general purpose registers from in a vector machine. You can think of it that way, except they store vectors as opposed to scalars, right? Okay, so let's also contrast the SIMD processing with VLIW. Remember, VLIW we discussed, and VLIW is also very important. You can see that in VLIW, multiple independent operations are packed into a long instruction. With a single program counter, you're fetching multiple operations. Yes, they're independent. So multiple operations is there. Independence is there, just like SIMD. But the major difference is in VLIW, you're fetching different instructions, right? You can see it's completely different instructions. These are completely different operations. And we're feeding it into concurrently executing processing elements, right? So clearly, VLIW, we covered it. Compiler packs these into a long instruction. But actually, SIMD array processing is very similar to VLIW. You still have a single program counter, but you don't have multiple different operations packed. You have a single operation, add. And add specifies how many elements and which vector register it's supposed to, the processor is supposed to do the addition on. So your program is actually simpler, as you can see. A single add specifies 4 additions. In this case, if your vector length is 4, for example. And you can see how it gets unrolled, let's say, if you will, to multiple different elements additions. So element addition for the increment of 0th element is done in this processing element. The increment of the first element is done in this processing element, and ... etc. Okay, so keep this in mind. Keep this picture in mind. SIMD array processing and VLIW are actually very similar to each other, except they're very different. Very similar in the sense that you can do multiple independent operations concurrently specified by the same program counter. Different in the sense that these are irregular operations that are completely different in VLIW, whereas you're operating on vectors in SIMD. And that's exactly why Josh Fisher, when he developed VLIW, he contrasted his work to array processing, as we will see also, as we have already seen actually. Okay, so let's go now into more detail. A vector. So let's talk about vectors from a programming perspective, right? Clearly, and we already talked about it, but I want to pictorialize some of these concepts. A vector is essentially a one-dimensional array of numbers, right? And two-dimensional arrays become matrices, as we will also see in a little bit. But many scientific and commercial programs use vectors. This is a boring example. You're basically taking 2 vectors, AI, BI. The size of each is 50 elements, as you can see. And you're doing element-wise averaging, storing the result into a C vector, as you can see. Okay? And you can see similar code, even more complicated code in many, many scientific programs. In fact, what we discussed last time, matrix multiplication, for example, convolutions using matrix multiplication is implemented using vectors. So you could actually do all of those matrix multiplications that we discussed that you did on systolic arrays, you could do it on GPUs, SIMD processors, and we will see an example of it. Not matrix multiplication, but we will see this averaging. But matrix multiplication is really no different. So a vector processor is essentially one whose instructions operate on vectors rather than single or scalar data values. Scalar means single data, basically. Vector means multiple data elements. So basic requirements for a vector processor are you need to load and store vectors. So you need vector registers that can contain vectors. So I've shown you examples of those vector registers. We're going to see more and more. You need to operate on vectors of different lengths, meaning that you should be able to set the vector length register. And vector length register specifies how many operations each instruction specifies at a given point in time. And the maximum can be the hardware vector length. Okay, but the software can set the vector length to something less than or equal to the hardware vector length, allowed vector length, basically. Okay, we will see this. And then the elements of a vector might be stored apart from each other in memory. And this is going to be important. I'm going to illustrate it in the next slide. This is called a vector stride register. Basically, vector stride register specifies what is the distance in terms of memory words between the different elements of a vector in memory. So stride is formally defined as the distance in memory between two elements of a vector. And this is going to be important because whenever you want to load a vector from memory, the elements may not be consecutive words, right? The elements may be actually nth consecutive words, right? Every n word, so element 0, element n, element 2n, etc., could be the elements that we want, because that's how the data is stored in memory, as we will see in a little bit. So you should be able to specify how you load this from memory, because vector loads will operate on taking one base address and incrementing it. Incrementing is fine if the elements are consecutively stored in memory, but incrementing it by one is not fine if the elements are far away from each other by n bytes or n words, depending on how you address memory clearly, as we discussed earlier. Then you need to increment your base address by n every single time you want to load one element, right? Okay, so this is something that's important. That's why let's take a look at a vector stride example from matrix multiplication. Let's assume we have A and B matrices. Both are stored in memory in row major order. Okay, row major order. Have people learned about row major versus column major orders? I don't know. Maybe you can tell me. Okay, no. Okay, you will see it. That's good. Interesting. I would think you may learn it in parallel programming, but not necessarily. Okay, but basically, row major order means that consecutive elements in a row are in consecutive locations in memory. It's very simple. So if you look at here, this is one matrix, right? A0 and B0. A0, if you look at row 0, well, the matrices are A and B. A0 is row 0. You can see that row 0 has 6 elements, and they're in consecutive locations in memory. So for example, A0 is this element is at base address plus 0 word address. This element has base address plus 1. This element has base address plus 2, base address plus 3, ... And then you store the next row in the next element, 6 over here. So this is row major. If you were doing column major, consecutive elements in a column would have been in the same in consecutive locations in memory. So this wouldn't look like this. This would have looked like 0 here, base plus 1 over here, 2 over here, 3 over here. So column major says consecutive elements in a column are stored in consecutive locations in memory. Okay. So B0 is also stored in row major, as you can see. So let's take a look at them in linear memory. So basically what I said is illustrated over here. A starts at some base address A, and you can see that consecutive locations belong to the same row. You get to the next column only at location 6, base plus 6. B also starts from somewhere in memory. Clearly, I couldn't put all of the elements over here, but imagine that A continues over here. B also starts from some location, some base address in memory B. And you can see that the consecutive 10 elements are in consecutive locations. And the next row, row 1, B1, starts from base address B plus 10. Okay. So you can see that this is a 4 by 6 matrix, this is a 6 by 10 matrix, and the multiplication produces a 4 by 10 C matrix. I'm not going to show it over here. But let's multiplication. What is multiplication? Multiplication is the dot product of each row vector of A with each column vector of B. Okay. So why are both row major? I thought they're stored differently. Well, this is what the programmer decided to do. And programmers can do it, right? certainly, both can be row major. Okay. So why isn't the base address place address +4 here? Don't you operate on 32-bit words? So basically, it depends on whether you are byte addressable or word addressable. Here, in this case, I don't actually show you the addresses here. These are the values. Well, these are the addresses of the words, let's say. These are word addresses. Think of these as word addresses. But your point is absolutely true. If you're operating on bytes, then it should be +4 every single time. Okay? So you're absolutely right. Okay. So if you're actually doing the multiplication, what you're doing is you're doing dot product of each row vector with the with each column vector of B and storing the result in one element of C. So to be able to do that, you need to load first A's row 0 into vector register 1, 6 elements. So your vector length is 6 in this case. So basically, you take those 6 consecutive things. So each time you need to increment the address by 1 to access the next column, as you can see. And access have a stride of 1, which is nice. Okay. But if you want to load B's column 0, you have some trouble into vector register 2, let's say it was assigned. So each time you need to increment the address by 10 to access the next row, as you can see, because you need to go through this element, this element, this element, this element column. Okay. So access have a stride of 10. Now you need to change your stride when you're loading A. When you're loading A, your stride should be 1. When you're loading B, your stride should be 10, and you need to have a change of stride in between. Okay, so let's go back to one of the questions that was asked. Why is B stored in row major? As I said, programmer did it this way. If programmer stored B in column major order, stride would have been 1, right? And I will let you think about it, because the consecutive elements of B would be 0, 1, 2, 3, 4, 5, 6 over here, right? Which would have been nice. 0, 1, 2, 3, 4, 5, not 6. 6 will become over here, which would have been nice. But for various reasons, that cannot always be done, right? Because you don't always operate on B as a second element of the second vector to multiply. It could be the first vector to multiply sometimes. And then you're back to the same problem, right? Basically, there's no good way of getting around this problem. Sometimes you will have to operate on a matrix and consecutive columns of a matrix when the matrix is stored in a row major order, like we're doing with matrix B over here. So this is the concept of stride, basically. We will see its impacts on accesses soon. Ideally, what you would like is consecutive elements are in consecutive locations, because this stride was going to cause us problems like bank conflicts we will see. And also another problem is changing the stride register, as we will see. Okay, but let's talk about vector processes a little bit more before we go into more detail. So a vector instruction performs an operation on each element in consecutive cycles. Vector functional units are actually pipelined. Each pipeline stage operates on a different data element. Because each data element is independent of each other completely, each operation is completely independent of each other, you can pipeline these vector functional units deeply. And you can pump in one element at a time, and your pipeline could be as long as possible without the penalties of a long pipeline. So vector instructions allow deeper pipelines because you don't have any intra-vector dependencies. So there's no hardware support needed for interlocking within a vector. You know that these operations are completely independent of each other because of the programming model. It's SIMD. It's beautiful. There's no control flow within a vector because you know that you're supposed to do all of these operations. There are no branches, basically. You just have a vector length. If your vector length says 64, you have 64 operations to do. No branch. Known stride allows easy address calculation for all vector elements. Basically, that's important also. If your elements are laid out nicely in memory with a known stride, it enables easy loading or even early loading or prefetching, in other words, of vectors into registers or cache or memory even from somewhere else, right? Okay, keep this in mind. But still, consecutive, like a single stride of 1 is better. Of course, this depends on how your memory is also laid out, but a stride of 1 makes things easier in general because you don't need to span multiple large distances in memory. Okay, let's talk about advantages and disadvantages of vector processes before we go into more detail and program these a little bit. So there are no dependencies within a vector, so pipelining and parallelization work really well. As a result, you can have very deep pipelines without the penalty of deep pipelines because there are no dependencies, no control flow dependencies, no data dependencies. Remember, these are the problems with pipelines. Resource dependencies still exist, so you need to solve them somehow. And each instruction generates a lot of work, a lot of operations. So this reduces the instruction fetch bandwidth requirements. You don't need to fetch a lot of instructions. And this amortizes the instruction fetch, decode, and control overhead over many data elements. As a result, this leads to high energy efficiency per operation. So SIMD processors like GPUs are extremely energy efficient if you're doing the SIMD operations, basically. So this is the reason, because you amortize the control overhead, instruction fetch overhead over many, many data elements. No need to explicitly code loops. Basically, there are fewer branches in the instruction sequence. We will see this in the code example in a little bit. And you have a highly regular memory access pattern with a certain stride. But if your stride changes, that also changes, as we said, right? Okay. So this is important. This is why ideally you should have only one stride, but you cannot get around it, because sometimes you access one data structure in one order, and sometimes you access the same data structure in some other order. That leads to different strides. As a result, your memory access pattern becomes irregular if you look at multiple different strides at the same time. It's still regular, but it's harder to deal with. Okay, so of course there are disadvantages as well. Basically, this works only if parallelism is regular. Basically, you have data or SIMD type parallelism. So if you have vector operations, that's great. But if you don't have vector operations, you're very inefficient if it's irregular. For example, how about searching for a key in a linked list? This is actually irregular because you need to, your addresses are dependent on previous addresses you generate, and you don't have much parallelism. This actually does really badly on vector processors, for example. So that's why when Fisher introduced the very, very long instruction word architectures, he wrote this: to program a vector machine, the compiler or handcoder must make the data structures in the code fit nearly exactly the regular structure built into the hardware. That's hard to do in the first place and just as hard to change. One tweak and the low-level code has to be rewritten by a very smart and dedicated programmer who knows the hardware and often the subtleties of the application area. So that's going to be very important, as we will see multiple times in this lecture. We're going to quote some examples, and if you have bank conflicts, for example, it's not going to work very well. Often the rewriting is hard, etc., as he says later. And again, this is the recommended paper. This is directly from your recommended paper from last time. Now, let's also talk about Amdahl's law a little bit while we're at it. Basically, Amdahl's law says there is a parallelizable fraction of a program, and that's infinitely parallelizable. Assume that. And there's a non-parallelizable fraction of program, which is 1 minus f. And your speed up, the best speed up you can get in this sort of parallelizable and non-parallelizable fraction is this. You cannot parallelize the 1 minus f part, but you can parallelize f by dividing the amount of time that takes with n, where n is the number of processors. It could be the number of processing elements in this case. So as n goes to infinity, this f over n goes to 0. So your speed up becomes 1 divided by 1 minus f, right? So if your parallelizable fraction is 50%, your maximum speed up possible as n goes to infinity is only 2. Sounds bad, right? 50%. If your parallelizable fraction is 90%, f is 90%, as n goes to infinity, this equation evaluates to 10x. So you get 10x speed up, which is not bad, but you're putting infinite number of processors. Okay. If your parallelizable fraction is 99%, your maximum speed up is 100x as n goes to infinity. So we look at this bottleneck, Amdahl's law like this. Basically, you have some thread that looks like this on the right. So there's a parallelizable part, as you can see. Here we actually have 1, 2, 3, 4, 5, 6 elements. But there's the non-parallelizable part at the beginning and at the end. And if that non-parallelizable part at the beginning and at the end becomes huge, then it doesn't matter how much your n is in the parallelizable part over here. You'll get a small number for speed up. And that's why he wrote the paper that you're going to review. Basically, maximum speed up is limited by the serial portion or serial bottleneck that's non-parallelizable. It's really bottlenecked by 1 minus f in the end. And all parallel machines suffer from the serial bottleneck. So keep this in mind, because we're going to actually see a lot of examples of this today. So the other limitation of vector processors is memory bandwidth, or memory can easily become a bottleneck, especially if compute and memory operations are not balanced. So if you have, for example, one memory operation for one compute operation, that's not good. Then you need to actually access memory for every single compute operation. But if you have 200 compute operations for one memory operation, then this is called the arithmetic intensity of the program, compute memory operation balance. Then you may actually have a less of a bottleneck. So if data is also not mapped appropriately to memory banks so that you can actually fetch different data elements concurrently or in consecutive cycles from memory, then you also have a bandwidth bottleneck as well, memory bandwidth bottleneck as well, right? Okay, so there's one question. Isn't the parallelizable part of a program only parallelizable to a certain extent and not infinitely most of the time? That's an excellent point. Yes, absolutely. So, but Amdahl gives the benefit of the doubt to the parallel processor and says, okay, and I throw whatever to this parallelizable part and I get speed up. But you're absolutely right. And we discuss in an advanced computer architecture course why this is not parallelizable. And that makes parallel programming even harder, actually. But even if the parallelizable part is infinitely parallelizable, you have the serial bottleneck. That's the point of Amdahl's law. Even if you give the benefit of the doubt that I can infinitely parallelize this parallelizable part, I still am bottlenecked by the serial part. Okay, very good point. That's why it's important to have good serial processors as well. Okay, so let's take a break right now, actually. We're going to cover vector processing in more depth. I'm going to take I guess 1 minute shorter break. Let's take a 9-minute break today because we have a lot to cover. We'll be back at 15:11. Keep the good questions coming. I see some more questions asked, but let's see if we can answer them. I don't know where they come from. Konstantinos is putting them. But we'll be back at 15:11 to continue more on vector processing. Okay, I think there was one question in chat that asked, can the stride be irregular? I'm not seeing on this, but I see it over here. So that's a good point. Basically, no, there's only one stride register in these machines, but basically there are no multiple stride registers that you can use. But I think what you're getting at is, can you use multiple different stride registers potentially? That's a more advanced vector processor, and it's not done in at least the traditional vector processors. So unfortunately, irregular strides are not allowed, but we will later see index loads or index stores, gather and scatter instructions that go through indirection to load values scattered across memory, and so that they can gather them into a single vector register. But we will cover that toward the end of this second part of the lecture. So basically, each vector data register, I mean, we already discussed active vector registers, so I'm going to go through this relatively quickly. Vector data registers are vectors, essentially. You can have many of them. There are also vector control registers, vector length, vector stride, vector mask, and maximum vector length can be n, as we discussed. This is the maximum number of elements stored in a vector register. So that's dictated by that, because this is really a hardware limit, as you can see, right? You cannot store more elements than n in a single vector register. There's also the vector mask register, which indicates which elements of vector to operate on. So this is going to be important because this is going to be conditional execution. We're going to be able to implement operations conditionally on different vector elements based on this vector mask register. For example, you can set the vector mask based on some condition. Whether some vectors ith elements is true, vector mask register's ith element will be set to true, for example, or whether some vectors ith element is false or not 0, then vector mask register could be set to 1. Basically, this decides which elements of a vector, as indicated by the vector mask register element, will be operated on or not. That way, you can actually do masking of different operations, right? Couldn't you store the length of the current vector in the last cell of the vector register to save hardware? Why do you need a register? Because you need to manipulate it. You need to manipulate vector length register separately. It's not really, logically, it's not really what you do. It's not really what you do with a vector, basically. Okay, as we will see. As we have seen earlier, actually, you need to manipulate the vector. Well, that was a stride. That was not the but basically, you need to manipulate the length register, because sometimes you may want to operate on 8 elements of a single vector register, right? Sometimes you may want to operate on 16 elements. Sometimes you may want to operate on 32, etc. You could make it arbitrarily different if you make it programmable. Okay. So vector functional units, we already discussed this also. I've already given you an example that looks like this: V1, V2. Basically, you stream different elements of the vector in consecutive cycles into a vector functional unit, and you stream the data out of the function unit into a destination vector register. Basically, you can use a deep pipeline to execute element operations, fast clock cycle. And the control of the deep pipeline is simple because elements in a vector are actually independent of each other. So in this example, the multiply is 6 stages, as you can see over here. And it could be even more. But this happens because the elements are completely independent. There are no control or data dependencies between these different operations that you're feeding into the vector functional unit. Okay, so this is an example of vector machine organization. I'll go through this relatively quickly. And this is one of the earliest supercomputers, the Cray 1 system. As you can see, there's a vector unit. There are vector registers attached to 8 vector registers, 8 64-element vector registers. So maximum vector length was 64 over here. And you had 64-bit elements. And you had 16 memory banks. We will get to memory banks soon. But they also had 8 64-bit scalar registers. So scalar part also very important. And they also had address registers to access memory. So it was a heterogeneous machine, if you will. It was not just a SIMD, single instruction multiple data machine. SIMD was just a part of it, but there was also a scalar part because different computations fit different types of execution: SIMD execution, scalar execution, and address generation execution. That's why they had this heterogeneity. And this was actually the fastest scalar machine of its time because they realized that scalar part is a sequential bottleneck. So they made this the highest frequency and most one of the most efficient machines of the time. And I recommend looking at this Cray 1 paper to know more about. And you can see they also talk about how they design the compilers, which we will talk about toward the end of this particular lecture briefly. So they had a parallelizing compiler or vectorizing compiler that vectorized innermost do loops, essentially. Okay, are there architectures with a two-dimensional address space to avoid bank conflicts when operating on two-dimensional data? Okay, so that's a very good point, but I think it's beyond the subject of this course. Yes, there are some architectures that can operate on two-dimensional, but vector machines are, at least the general purpose vector machines and SIMD machines are not. But you're thinking well, basically. Now you're thinking, what if you have two-dimensional data in an array, for example, or in a matrix? How do you operate on it? But we're not going to get into that. So you need to take an advanced architecture course to discuss those. Okay, I would also recommend that you go and take a look at the later version of a Cray machine, an ETH cab eFloor. You can find it over there. You can actually find some information about it also. And you can see that that looks like Cray 1 as well, except it's a better version of Cray 1, if you will. You can see there's a vector mask register, 64 bits, vector registers over here. Memories are also larger than Cray 1. But you can see the basic structure is very similar to Cray 1. Okay, there's scalar functionals, etc. So you have different types of registers: vector registers, scalar registers, and address registers, as you can see. And there are also other registers, which I'm not going to go into. Okay, so I'm not going to go into the details of it, but you can also look at the different clock cycles. So their clock cycles were actually quite good compared to 1985, as you can see over here. Because that is because the vector machines can be very easily pipelined. And you can see the different functional units and different amounts of time, different things, different types of operations actually take. But again, I'm not going to go into the details of it. Clearly, this is beyond what we're discussing. But these are real machines. That's the whole point of this. These are real machines, and these are supercomputers of the day. That's why they were designed, so that they can do big scientific calculations on big vectors. And that's why they have large memories, also large I/O subsystems as well. Okay, so I think no discussion of Cray computers should go without mentioning Seymour Cray, who actually founded the Cray research to develop these supercomputers. He was a leader in supercomputer design. And after he designed all of these machines, he's known to say, if you were plowing a field, which would you rather use, 2 strong oxen or 1,024 chickens? And basically, I think his answer was 2 strong oxen, 2 big animals, basically, like very powerful processors or very many simple processors. Basically, he figured out that after all of these designs, memory system was a big bottleneck. And to tolerate a lot of the memory latencies, you actually need some powerful processors in your system. So later, he was actually founding a startup, but he passed away too early to actually be successful in that startup. And this is just an analogy for you. Which one would you plow a field with? Probably the left one. So this also points to one downside of the SIMD engines, right? You have these very powerful parallel processors that are good at one thing, but they may not be good at plowing a field, which is a very hard, irregular task potentially, right? Okay. Okay, so that brings us to memory banks, because memory is going to be very important. We should be able to fetch or load and store vectors from memory, and that's going to pose a bottleneck. So you may, for example, have 1 million vector elements. Okay, you can imagine potentially building 1 million adders to actually do the additions. But how do you actually do the loading from memory becomes harder, because now do you really have 1 million different ports to memory? How do you actually start 1 million accesses? If every single memory access takes 1 cycle, that's great, because you can actually start 1 access 1 cycle, and every cycle you get 1 element. That's fine for a vector machine. That's not fine for an array machine, array processor, as we discussed. But for a vector processor, all you want is 1 element per cycle throughput. But if your memory takes not 1 cycle, it takes 10 cycles, How do you sustain one element per cycle throughput? You need some concurrence in your memory system, basically. That's why these folks actually, these machines had actually very sophisticated memory systems, 16 memory banks in this case. Okay, basically loading and storing vectors from and to memory requires loading and storing multiple elements. Elements are separated from each other by a constant distance. That's our assumption, stride. If they're not constant, we will do something else, as we will see. Assume a stride is equal to 1 for now. Let's handle the simple case. Basically, consecutive words are in consecutive locations, right? And I'm talking about words right now. Don't think about byte addressable. Byte addressable just makes things multiply by 4, right? So elements can be loaded in consecutive cycles if we can start the load of one element per cycle, basically. That's the idea over here. And we're going to enable this by banking. So basically, we would like to sustain a throughput of one element per cycle. Remember, vector loads one element per cycle in a vector processor. We would like to be able to do that from our memory system. But of course, how do we achieve this with a memory that takes more than one cycle to access? If it takes one cycle, no problem. If it takes 2 cycles, well, now we have a problem, right? And the answer people have developed is to bank the memory. Later, we will see other answers, more expensive answers. But banking the memory is a cheaper answer, as we will see now. And we like to bank the memory into separate structures. And we like to interleave the elements across the banks, meaning 0th word is in bank 0, word 1 is in bank 1, word 2 is in bank 2, word 3 is in bank 3, ... etc. Right? So that way, you can access bank 0 in the 0th cycle and start the access of word 0, which may take 11 cycles, let's say. And then in the next cycle, after you access bank 0, you access bank 1, start the load of word 1 from bank 1. That may take 11 cycles also, but you're parallelizing a good chunk of that latency. Okay, so banking looks like this basically. Basically, instead of having a single monolithic memory, you divide into, in this example, 16 banks. In the general case, n banks, where n is a power of 2. And you can see that each bank has a memory data register and a memory address register in a fashion that's very similar to what we have seen with memory earlier. And basically, you can write to one memory address register in one cycle. So if you interleave the words consecutively so that you can actually access consecutive words in consecutive cycles from different banks. So if your memory takes 10 cycles, for example, by having 16 banks, you can sustain one element per cycle throughput from your memory every cycle, assuming the consecutive words are in consecutive banks. Right? That's the good part. So your word 0 is in bank 0, word 1 is in bank 1, word 2 is in bank 2, ... word 15 is in bank 15. And at cycle 0, you access bank 0 to get word 0. At cycle 1, you access bank 1 to get word 1. At cycle 2, you access bank 2 to get word 2. You start the accesses, but the accesses may take 10 cycles, let's say. Soon we will see 11 cycles. The first data arrives back at 11th cycle. Now you can actually feed it to the CPU, to feed it to the next execution unit that needs it. The next element comes at the next cycle. The next element comes at the next cycle. So by starting the accesses in consecutive cycles, you're going to get the data n cycles later in consecutive cycles, right? That's the idea, basically. You sustain one element per cycle throughput, even though your memory access latency, bank access latency is more than 1, but you have enough banks so that you never have a gap in your throughput. Basically, you always get one access per cycle. Now, of course, this requires your data mapping to be nice. If your stride is 1 and consecutive words are mapped to consecutive locations, that's great. Okay, we're going to get back to this. But basically, the key idea is memory is divided into banks that can be accessed independently. Independently meaning you start an access independently. You cannot do accesses in the same cycle at the same time because we have a single address bus, single data bus. Okay. And the goal is really banks share the address and data buses. They have single address bus and single data bus to minimize the ping cost. You can start and complete one bank access per cycle. I'm going to show you another example soon. Now you can sustain n concurrent accesses if all n go to different banks, right? Okay, keep this in mind and you can also study it on your own. But this is an example of a vector memory system. This is how you actually generate the address. If you have a vector load, you have a base address as we discussed. You have a stride. Assume stride is 1 right now. Every cycle, you input base address plus stride. Initially, base address plus 0, of course. And then you increment the base address by the stride. and then next cycle you input it into the memory system, and then next cycle you increment that by another stride, and then you keep doing this basically until you do it enough times that's equal to the vector length register, right? As we discussed, because you want to load the vector length number of elements into a vector register. Okay, so next address is simply calculated as a previous address plus the stride, so it's very regular, as you can see. Now, if stride is 1 and consecutive elements are interleaved across consecutive banks, as you can see, and the number of banks is greater than the bank latency, then we can sustain 1 element per cycle throughput. Now, if any of these is different, then you may get a different answer. For example, if the number of banks is less than the bank latency, then you will not be able to sustain 1 element per cycle throughut, because at some point you will need to stall. Okay, so you really want number of banks greater than your bank access latency. So if your bank access latency is 11, in Cray 1 it was 11, they basically put 16 banks so that they could have enough banks to cover for the 11 cycle latency, right? Okay, so if your bank access latency is 33, how many banks do you need to have so that you sustain 1 element per cycle throughput? Any takers? Your bank access latency is 33. Yes, somebody answers 33. So basically, you're a mathematician. If you think about the implementation of it, so your answer is correct, except the hardware to build it is very hard because we're using binary numbers, right? So the answer in a much more easily buildable hardware is 64. But your answer is mathematically correct. So there's an answer of 64 also that I see. So that gives you the distinction between the mathematicians versus the engineers, let's say, between you. For a mathematician, the answer is 33, absolutely, because you only need 33, right? But then how do you address that? Because we have binary numbers. Addressing an odd or a non-power of 2 location in memory or bank number is not easy, because we're going to use the address to determine which bank to go. Part of the address will be, some bits in the address will be used to essentially decide which bank that address maps to, right? The bottom bits after the word in our case, because we said your interleaved consecutive elements are interleaved consecutively. But basically, 33 is difficult to build. That's why we go to the next power of 2, which is 64, right? Okay, so very good answers. That's good. So let's take a look at an example of how we actually do this. But we're going to get back to this actually. We're going to get back to this banking and stride later, because this causes problems. Okay, let me give you another example. You have 16 banks like this. This example has 16 banks, right? Consecutive elements are interleaved across banks. So element 0 or word 0 is here, word 1 is here, word 2 is here, word 15 is in bank 15. Word 16 is in bank 0 again, right? Basically, you do that consecutive elements are in consecutive banks mapping. This is great if stride is 1. What if your stride is 16? Now you have a problem, right? Because if your stride is 16 and your consecutive elements are in consecutive banks, exactly the elements that you would be fetching from will be mapped exactly the same bank. So element 0 is here, element 15 will be here, well, element 16 will be here, element 32 will be here, element 48 will be here, ... So basically everything gets mapped to the same bank. So you're back to square one. So your stride is not relatively prime with the number of memory banks. It's actually the real condition. Your stride needs to be relatively prime with the number of memory banks, so that assuming consecutive elements are interleaved across consecutive locations, of course, consecutive words are interleaved across consecutive locations, so that you don't get bank conflicts. So this is why this is a very difficult problem, because programs may have different strides, right? So now your performance is very much dependent on the stride that your program uses and the number of banks you have in your memory system, okay? And how you do the data mapping across those banks. Clearly, you can easily go to a 1 element per cycle throughput, or you can go to 1 element per 11 cycles throughput, assuming each element takes 11 cycles, as we briefly mentioned. Okay, so that's why this is extremely important. This is also important in a VLIW machine, by the way. That's why these folks who designed the VLIW compilers initially looked at memory disambiguation mechanisms in their VLIW compilers. And if you remember the last lecture where we talked about the Bulldog compiler very briefly, they had a memory disambiguation mechanism where they tried to basically map the data accessed by different instructions into different banks. That's what you need also here. The data that needs to be accessed by different operations in a vector should be mapped to different banks, assuming your access latency to the banks is more than one cycle, or assuming you want concurrent loading of them. Array processors actually put even more pressure. But then you're also operating on many possible vectors, so this problem becomes more complicated as your parallelism actually increases. Okay, so let's take a look at a scalar code examples, and we're going to turn it into vector, and we're going to improve its performance. So it's going to be fun, hopefully. And the example is very simple, so that we make it actually simple. This is, again, element-wise average. Programs actually do this, as I said. Basically, we're going to element-wise average two vectors of length 50 in this particular case, as you can see, and store the result into another vector. Okay, sounds good, right? These are simple operations. That's why we picked it. Scalar code looks like this. Basically, in a SIMD machine, single instruction, single data machine, with some complicated instructions, as we will see soon, this actually leads to this scalar code. Basically, we set R0, R1, and R2, and R3, which are the loop induction variable, and then the base addresses of the arrays. Okay, one cycle each. So these the numbers on the right actually give you the cycles, number of cycles to execute each instruction. It's going to be equivalent to the number of cycles we do in the Cray 1 machine, actually. And then we start a loop. Basically, a loop does this. You basically first load the elements of A, and then you load the element of B. You auto increment the addresses so that you don't have a separate instruction for this. So actually, I'm minimizing the instructions in the scalar machine. Basically, whenever you do this memory operation, you first load from the memory location specified by R1, which is the base address of A, and then you automatically increment R1 by 1. In this case, we're assuming word addressable machine, okay? And you automatically increment R2. So basically, we're not spending more instructions just to increment the address. We're doing it as part of the load. This is called load with auto increment addressing. There's actually a special name for it, and vector machines actually had this, so that you could actually, actually some scalar machines also had it, but I'm not going to talk about that. So basically, this saves some instructions clearly. But now we've loaded each element in the loop of essentially AI and BI, depending on which loop iteration we're in. It takes 11 cycles to do each, as you can see. And then we need both to execute this add. After the load is done, add takes 4 cycles, as you can see. That's a simple add. And then after the add is done, we can shift by 1. That's dividing by 2 to the right, shift by 1 to the right. That takes 1 cycle, simple operation, as you can see, because it's shift by 1. And then we store the resulting value, R7, into array C's ith element, and then do auto increment addressing again, so that the next iteration can go to the next location, next address in the array, right? And then we have this fun instruction called decrement and branch if not 0, R0. Basically, what this does is it decrements R0 and branches if the R0 is not 0, okay? So it's first decrements the R0 and then checks if it's 0. If not 0, then it basically jumps to X. So you can see the latency is 2 over here. Basically, this loop is guaranteed to execute 50 times, assuming you set R0 to 50. And we did over here. So this is scalar code, and you can easily write it in MIPS also with more instructions, because MIPS doesn't have this decrement, BNZ, and auto increment addressing. So MIPS actually will have more instructions. So let's take a look at this first. So how many instructions do we have when we execute this code? How many instructions are actually executed? Dynamic instructions. Static instructions, clearly you can see the number, right? Static instructions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Dynamically, though, it's going to be 304 instructions, right? Why? We have 4 instructions here. Each loop iteration is 1, 2, 3, 4, 5, 6 instructions. And we have 50 iterations of the loop. So this is 300 instructions plus 4. So that's a lot of instructions. And each instruction is doing essentially almost the same thing, right? Each loop iteration is doing the same thing, basically, on different data. So essentially, our SIMD machine is going to save us a lot of instructions. We're going to reduce that to 7 soon. But before we do that, let's take a look at how long this code executes on a scalar machine. I'm not going to go into out-of-order execution here, but out-of-order execution it could be actually useful by parallelizing different loop iterations, unrolling the loop internally in the machine. So it could actually improve performance. But I'll leave that to you to do that exercise, how long it takes to do this in an out-of-order machine with some assumptions. But let's take a look at simple machines first. Scalar execution time on an in-order processor with 1 bank. This is very, very simple. Basically, you will see that it takes 2004 cycles to do it because we have 1 bank. Essentially, these are 4 cycles. each loop iteration is serialized because you cannot parallelize these two operations, even though they're independent of each other, as you can see, where the rest is dependent on each other, right? So basically, each loop iteration takes 11, 22, 26, 27, 38, 40 cycles, and we have 50 of those. That's 2,000 plus one of each, 2,004 cycles. Okay, that's easy. Now, if you have a scalar execution time on an in-order processor with 16 banks, word interleaved, meaning consecutive words are stored in consecutive banks, now you can parallelize the first two loads in the loop, or pipeline them, right? Basically, these are independent loads, right? Because they're accessing different locations, clearly. What you can do is you can start the first load in the first cycle. You can start the next load in the next cycle, right? That way you can overlap the latency of the first load's 10 cycles with the latency of this 11 cycles. So basically, essentially, first load takes one cycle, if you will, right? So you really reduce the latency, effective latency of the first load to one cycle. And this is 11 cycles. So basically, if you do the calculation, the loop now takes 30 cycles because we've eliminated 10 cycles from here, right? It used to take 40 cycles. Now it takes 30 cycles because we've overlapped 10 cycle latency of this load with this other load because we have multiple banks. You didn't need 16 banks for this. You needed only 2 banks, right? Because you're doing only 2 loads in the scalar machine. So, but I just use 16 banks over here. You can, of course, have anything more than 2 banks. So if you do that, you get 1504 cycles. So clearly, having 2 banks or 16 banks gave you 500 cycles at some cost. But it's not bad also. Okay, now let's take a look at, well, why 16 banks? 11 cycle memory access latency. Having 16 banks ensures there are enough banks to overlap enough memory operations to cover memory latency. It doesn't hold in this particular case, but it will hold in our vector processor, as we will see soon. In this case, you can actually get away with 2 banks, as we discussed, because you're doing only 2 loads, right? Okay, now let's take a look at the notion of vectorizable loop. So the loop that we saw was actually a vectorizable loop. What does this mean? A loop is vectorizable if each iteration is independent of any other iteration, basically. So this is an example, as we saw. And if we vectorize this loop, this is what we will get. Each instruction is latency. It will look like this. Basically, our vector length is 50. Our vector stride is 1, because we said consecutive elements are in consecutive locations. Stride is 1. Then we do a vector load into vector register 0, starting from address A. That will take 11 plus vector length minus 1 cycles. The first element of A is loaded after 11 cycles. And then in consecutive 49 cycles, we get the remaining 49 elements of the vector. And then we do a vector load into vector register 1, B, which again takes 11 plus vector length minus 1 cycles. First element comes after 11 cycles. And then in each consecutive cycle, you get 1 element. Okay, that's how it's supposed to be. Assuming you have enough banks, again. We're going to assume that. And then you have vector add. Basically, you take the each element basically you add 2 vectors and do it element-wise. The first element is added after 4 cycles, and each remaining 49 pairs of elements are added in consecutive 41 cycles after that. And then you do the shift. You can see that these are dependent on each other. You take V2 and shift right by 1. The first result comes after 1 cycle, and then the remaining results for different elements come after 49 consecutive cycles, 1 by 1, each cycle. And then you do the store, again, the same story, basically. So these are the instructions you can see. And that's it. There are no branches, as you can see, because we coded the loop in a vectorized way. Each loop iteration is essentially an element in a vector, basically. And you basically execute multiple different SIMD instructions to execute the loop iteration over here. And we have only 1, 2, 3, 4, 5, 6, 7 instructions, of which only 5 are vector instructions, as you can see. 1, 2, 3, 4, 5 are vector. 2 of them are scalar instructions over here to set up the vector length and vector stride register. So we already saved a lot. Only 7 dynamic instructions, which means that we're not fetching 3 or 4 instructions. We're fetching only 7 instructions. We're decoding only 7 instructions. So we got rid of a lot of inefficiency in the execution of this loop, as you can see. And that's one big advantage. And that directly translates to energy. No question about that, because you really get rid of the control overhead. And this is a small vector size. This is 50, right? In some machines, you could actually have one up to 1024, for example. Okay. Okay, so this is basic vector code performance. Let's take a look at performance now. We talk about energy a little bit. Now let's take a look at performance. Let's take a look at the basic performance, meaning no forwarding between different vector functional units. Essentially, This is called chaining. It's a special terminology in vector machines. But basically, chaining means forwarding of data between different vector elements. So whenever one element is available, you forward it to another functional unit. That's the idea. So basically, output of a vector functional unit cannot be used as a direct input of another if you don't have chaining. If you do have chaining, it can be used. Okay. So basically, the entire vector register needs to be ready before any element of it can be used as part of another operation. So you can see that this is very conservative, right? Vector elements are independent of each other. And if you look at over here, if you look at what we're doing, we have add, shift, load. We can start the first element's add after the first element's loads of A and B are complete in the first element part of vector register 0 and 1. Similarly, once add's first element is complete in vector register 2, we can start the shift. And then once that is complete, we can start the store. So basically, we don't need to have the full vector to be ready before we can start part of the next vector instruction. But we're going to assume conservatively that we don't even have chaining to begin with. Okay. So let's take a look. We're going to assume one memory port, one address generator. Oh, sorry about that. Something happened. One memory port, meaning you can only start one load in a bank. You cannot start two loads in different cycles in one bank. Two memory ports means you can start two loads. Two load ports, one store port means you can start two loads and one store and sustain them concurrently. Okay, but we're going to assume one address generator and one port per bank. We're going to change that in a little bit. And then we're going to assume 16 memory banks because it's going to be important. And we're going to assume word interleaving. Consecutive words are in consecutive banks. Okay, so that's going to be nice base. Okay, so this is the execution that we have. Because we're waiting for the entire vector to be ready. So this is the scalar instructions, one cycle each. This is the vector load of 50 elements. The first element comes after 11 cycles. The remaining elements finish after 49 cycles. But we cannot start the second load because we have only one memory port in this case. Maybe this is a bit okay. Maybe this is a bit conservative. Also, you could actually parallelize this over here, but this is the conservative version where we assume that we cannot start the next load, even though they're independent of each other. But bear with me. Even this is going to be faster than what we have seen earlier. So basically, the next load starts after the first load ends. It takes 11 cycles, the first element, and then the remaining 49 elements come after 49 cycles. And then the add can start after both of its data is ready. It takes 4 cycles to generate first element. And then the remaining 49 elements get generated in the remaining 49 cycles. And then the shift can start 1 cycle for the first element result, and then the remaining 49 cycles over here. And then store can start 11 cycles to write the first element to memory location, and then 49 cycles for each consecutive remaining elements. So even though, for example, we could have parallelized this load, starting it concurrently with this one, and I agree that you could have done it with 16 memory banks over here. This picture is a little bit conservative in that sense. But even with that not done over here, you get 285 cycles, which is quite good, right? I guess one of the reasons why we didn't do it over here is maybe you get bank conflicts, right? If A, yeah, exactly. Because A and B, we didn't really specify exactly where A's 0th element and B's 0th element are mapped, right? A's 0th element may be mapped to bank 0, B's 0th element may be mapped to bank 0 also. Then you cannot start B, absolutely. And we're assuming one address generator also. So basically, based on my assumptions, actually, this picture is correct. Because we're assuming one address generator over here. You can only generate one address per cycle. But again, maybe you could argue that you could do it over here. Yeah. So basically, you can optimize this with some assumptions that are added over here. But still, this is 285 cycles. So let's go back. What we have seen earlier. 1504 was the best we had. Now we have 285 cycles. We're already almost 6x faster. So that's the power of a vector processor, as you can see. But we're going to make it better. Now let's take a look at how to make it better. So we're going to talk about chaining. Chaining is essentially data forwarding from one vector functional unit to another. And this is the basic idea. A load produces one element. Multiply should be able to start with that element. Multiply produces one element result. Add should be able to start with that element. It doesn't need to wait for the entire vector. And pictorially, it looks like this. Vector 1 goes to load unit. Load unit actually gets the basically this is a load vector. You load consecutive elements in consecutive cycles into vector 1. while you get one element, you also forward it to the multiplication unit. And the result of the multiplication unit can get forwarded also to the add unit. So basically, you don't need to wait until all of the vector elements are done. You can just do element-wise forwarding to the input of the functional units. And that's the idea. And that's relatively easy to do. Of course, it's very similar to bypassing, right? Chaining is basically like data flow, like data propagation. Yes, I would say that. It's data forwarding. I would call it data forwarding. But again, data forwarding is like data flow, as we discussed in a pipelining machine. But yes, so basically, that's the idea. Of course, this adds some more complexity, but it's going to buy us some more performance, as you will see. So basically, what this will change? Data forwarding from one vector function into another. This is the scalar instructions. These are the two loads. Now, at the end of this 11th cycle of the second load, we have the first element of both A and B ready in vector 0 and vector 1. So we can start the add. And in consecutive cycles, we have the consecutive elements of B ready and A also ready, and we can do the add on those. So basically, we are overlapping the load and add by doing the chaining, as you can see. And then we're the result of add, the first element is ready after 4 cycles. Now we can do the shift, as you can see. The result of shift is ready after 4 cycles, but now we cannot start the load store because we're assuming only one address generator, which essentially assumes that the banks are busy. Banks have only one port. So basically, you cannot start the store because the banks are busy over here, okay? That's important to keep in mind. Okay, that's why I have this dashed line over here. So basically, overall, this leads to a much faster execution time because we're overlapping the load, add, and shift latencies and somewhat of a store latency also over here as well. So the execution time, if you do the math, goes down to 182 cycles by doing just vector chaining. And again, you knew the importance of data forwarding, so it's going to be very similar, but it's bought us about 103 cycles. Now, the question is, of course, always, can we do better? And now you need to look at the memory system. The rest of the parallelization is because we don't have enough ports in the memory system. So this vector load and this vector load cannot be parallelized or pipelined because their data is mapped to the same memory banks, and we have only one address generator, one port for each memory bank. This load and store cannot be pipelined because we have only one address generator and one port per memory bank. So what is the solution? Basically, add more ports. Add more ports so that we can start to access different addresses in the same bank concurrently. This requires two address generators concurrently, maybe 3, right? If you want to do multiple, more than 3. And we're going to do 3 actually. Basically, the strict assumption we had was each memory bank has a single port. And this is the memory bandwidth bottleneck that we were talking about earlier. Data clashed in the same bank, so we can actually only access one bank. But by actually having multiple ports, we can only access one bank for one address. If we actually add more ports, we can use multiple addresses to access the bank so that we can get multiple data elements at the same time. This is very similar to the register file that we saw, multi-ported register file, right? You can actually have multiple ported register files so that you can access source register 1 and source register 2 concurrently. That's what we're trying to do over here. We want to access A and B in different locations. So A and B are the banks here, right? No, the A and B are the vectors. Banks are 16. We have 16 banks. Okay, so basically, now we are assuming 2 load ports and 1 store port in each bank. If you do that, if you have 16 banks, like we assumed at the beginning of the code, now what you can do is you can complete the parallelize the 2 loads. Well, except for the first cycle, because remember, we're actually inputting 1 address per cycle, right? So basically, after you input the first address of this vector load, you input the first address of vector load B over here. And as a result, basically, even though A and B first elements are in the same bank, bank 0, because you have 2 ports in the bank, you can access them back concurrently. You can access them concurrently. Now you've overlapped almost the full latency of this load with this load. And we already overlapped add and shift. But this store also doesn't need to store, but because we also have a store port in each bank. So we have 3 address generators, 2 for loads, 1 for stores. As a result, you don't need to store as much. And the execution time is 79 cycles, as you can see. So, okay, I think you folks are answering each other's questions. That's great. Yes, that's what I was going to also say. I also already said it earlier. But basically, this is 79 cycles. So that brings us to from 182 cycles before. And of course, you can potentially optimize it as well. But so why does vector load have 2 ones? So these are, remember, these ones are not vector load. These ones are the scalar instructions, setting the vector length and vector stride. Keep that in mind. Okay, they were present in all of the figures, but I just didn't annotate them over here. Okay, so 79 cycles, that's a 19x performance improvement compared to 1504 that we saw earlier. So that's a very large performance improvement, and that shows you the power of a vector machine. Okay, now let's handle some issues. Basically, vector machines are both high performance and potentially energy efficient. But of course, they come at the cost of solving the memory bandwidth bottleneck. So solving the memory bandwidth bottleneck almost gave us 2x performance improvement in this case. And we don't even have irregular access patterns here, but we do have a lot of bank conflicts, assuming that A's elements are mapped in consecutive locations starting from A0 and bank 0. And B's elements are also mapped in consecutive locations starting in banks B0 in bank 0 also. You have essentially all conflicts between A and B, right? And these are not easy to resolve unless you add load ports, as you can see, and store ports. Okay, so there are a bunch of interesting questions to make this more general purpose. Now let's take a look at that. What if the number of data elements are greater than number of elements in a vector register? Now you need loops. Basically, you break loops so that each iteration operates on number of elements in a vector register. For example, if you have 512 data elements, 527 data elements and 64 element vector registers, now you need a loop where you have 8 iterations where vector length is 64 and 1 iteration where vector length is 15, right? That's what you need to do essentially. So you still have some control flow overhead, but you still amortize a lot of the overhead of instructions. But in the last iteration or the first iteration, usually the last iteration, you need to change the value of vector length, which actually cause a stall in the pipeline potentially. This is called vector strip mining for various reasons that I'm not going to go into, but basically you're strip mining the top of a mine, if you will, and it comes from this term over here, mining terminology, which I'm not going to go into. Okay, let's talk about some interesting issues that some of you point out. What if vector data is not stored in a strided fashion in memory? What if you have irregular memory accesses? How do you do that? And this happens, basically the idea is to use indirection. Remember the load indirect instruction from LC3 that we discussed a bunch of lectures ago? We're going to use something like that. We're going to use indirection to combine or pack elements into vector registers. And I'm going to give you some examples. These are called scatter and gather operations. And these are very important on vector machines that operate on sparse data, sparse vectors. So sparse vectors are vectors where a lot of the elements are zeros, for example. You don't want to operate on zeros in general. If you're doing matrix multiplication, for example, if an element is 0, there's no reason to do that multiplication with 0, right? Because that the result is, you know. So basically, doing so, this scatter gather operations helps with avoiding useless computational sparse vectors where many elements are zeros. Okay, so let's take a look at these gather scatter operations. So basically, we want to vectorize loops with indirect accesses at the core of it. And this is an example. AI equals BI plus C DI. Addresses are stored in the D vector, basically. And that you have n addresses over here. So basically, we're going to introduce an instruction called index load instruction, a load indirect, essentially. It's called also a gather. So what we will do is we're going to load indices in the D vector. And then we're going to load indirects from RC based using that D vector as the addresses, as the indices for the D vector. Instead of incrementing the indices by 1, we're going to use another vector register, D vector register, as the indices to increment the base address with. That's the idea, basically. And that could be irregular now, right? Because now you have an indirection. This D vector can specify any number to add to the base address, basically. And then load of vector B, and vector B is easy. And then we do the add, and then we store the result. So basically, key difference is this load indirect using some indirect indexing. So let's take a look at that, basically. So gather scatter operations are often implemented in hardware to handle sparse vectors or sparse matrices or indirect indexing, like what we see. This is a way of this could be a way of dealing with sparse vectors. You basically figure out which elements of the vectors are zeros and not include them in the D vector, basically. The index, not include those indices in the D vector over here. So let's take a look. Vector loads and stores use an index vector, which is added to the base register to generate the addresses. So what does this mean? Let me give you an example from scatter. Scatter means you take a packed vector and you scatter it into memory different locations based on some index vector. So let's say our index vector is 0, 2, 6, 7, meaning that the locations should be stored, and our data vector is this, and we're only looking at 4 elements over here. Basically, this data vector first element should be stored to a base address plus the index in the index vector. And that's what we do as a result of that instruction. The second element in the data vector should be stored to base address plus 2, because that's the second element in the index vector. The third element to the third data element should be stored in base address plus 6, as you can see. And the fourth element should be stored in base address plus 7. I just show you up to 7, but these numbers can be actually large also. So this way, you don't have to store to these locations, as you can see, and maybe they're all zeros and we don't care about them if it's a sparse vector, for example. This way, you can selectively store to arbitrary locations irregularly in memory. You can also gather, this is a scatter. Basically, you take the index vector and add the indices to the base elements in consecutive cycles, to the base memory address in consecutive cycles, and take each element, data element, to do the store. And this is the resulting stored vector in memory. Similarly, you can do this gather also, right? If your index vector is this and your stored vector is this, and you want to gather using an index vector, this is the value in consecutive cycles you fetch from base plus 0, and then base plus 2, and then base plus 6, and then base plus 7, basically. Okay? So that's the beauty of it. That way you can do indirect accesses. Okay, now we're generalizing. Let's talk about conditional operations in a loop. What if some operations should not be executed on a vector based on a dynamically determined condition? We actually saw the vector mask register, right? And again, this is an example. For example, we're iterating up from 0 to n. If the element that we're examining in AI is not 0, then we do the multiplication AI times BI and store the results in BI. So basically, it's a sparse vector potentially, right? AI is a sparse vector. And for 0 elements, we're going to skip the multiplication. How can you actually do this? So the idea is to do the masked operations in a vector processing. Vector mask register is a bit mask determining which data element should not be acted upon. Clearly, the data elements that are zeros should not be acted upon in this case, right? So you can code this nicely. And this is the code, basically. So you can load array A into vector register 0, like we have seen earlier, array B into vector register 1, and then set the mask register by checking each element of vector 0 and checking if it's not equal to 0. If it's not equal to 0, the element, the bit in the mask register will be 1. And then we do the multiplication. So basically, this multiplication is done only on elements where mask register is set to 1. So it's a conditional operation now, because we've set the mask register to, mask register is also 64 bits in this case, assuming it's 64 bits. It's a vector length, basically. Everything's vector length. You basically operate on the elements for which the mask value is set to 1. And that's what happens with the multiply. That's what happens with the store also. Once you set the mask register, the remaining instructions conditionally operate based on the values in the mask register. Initially, the mask register is all ones. That's the assumption, basically. Okay, so this is an example of predicate execution, basically. Execution is predicated on the mask bit, as you can see over here. The execution of each element of multiplication, vector multiplication over here, is predicated on whether the mask bit for that element is set to 1. If it's set to 1, you do the multiplication of the elements. If not, you don't do the multiplication of the elements, satisfying the code over here. Ditto for the store. It's the same thing for the store. Okay, so let's take a look at a more complicated example with masking, if then else. It's going to be essentially very similar, basically. This is a very simple loop, as you can see. If AI is greater than BI, then CI gets AI, otherwise CI gets BI, as you can see over here. So steps to execute the loop in SIMD code looks like this. We first compare A and B to get the vector mask register. Okay, I'm going to show you that with an execution. So basically, this is the comparison. Assume that these are the elements in the vector. I don't show all 64 over here clearly. I show some number. So vector mask register is 0. The bits in the vector mask register is 0 for this particular case because A is not greater than equal to B. In this case, A is greater than equal to B. So for cases where A is greater than equal to B, vector mask register will be 1. For cases A is where the opposite of 0, vector mask register will be 0. So that you can operate on the elements that you really care about. So in this case, we do a mask store of A into C first, basically. That's what this is. And then we need to complement the vmask. So basically, the first mask store uses this vmask because if AI is greater than or equal to BI, the vector mask bits are set, then CI should get AI, right? That's the mask store of A into C. Now, how do we execute the else part? That's the interesting part over here, clearly. We complement the VMask, right? Because it's the execution of the else part is exactly opposite mask of what we execute over here. So it's exactly opposite condition for this. So we complement the VMask. VMask complement becomes 1, 0, 0, 1, 1, 0, 0, 0. And then we use that mask to do a vector store of B into C. Okay, you can study this on your own. It's very simple once you understand the masking concept. But basically, you can operate on the vector mask registers by complementing the VMask. You can actually do even more complicated predicated execution operations if you have more complicated predicates over here. In this case, we have a simple predicate, as you can see. But it could be, for example, if AI is greater than or equal to BI, or AI is less than or equal to 5, and BI is greater than or equal to something. Basically, you can have a complicated VMask, and you can have a much more complicated control flow also. By manipulating VMask, you execute different operations in a vectorized manner. And this is the fun part of a vector engine. Clearly, if you don't execute something because the VMask is 0, you're wasting efficiency, right? Because you have a vector length. In this case, vector length could be 64, for example. I just made it up. And if all you execute is only one operation, because only for that element vector mask is set, you're losing 63 out of 64 slots of instruction execution. Basically, you're losing a lot of efficiency. And that's not good. And that's the Achilles heel of vector machines. If your code is irregular, where you have a lot of control dependencies like this, yes, you can convert it into vector instructions, but your efficiency very much depends on your vector mask. If your vector mask happens to be all zeros, well, actually, if all zeros is easy, you skip the execution. But if your vector length is 64 and your vector mask has only one set element in it, you're executing only one operation across 64 execution units. So your efficiency, this is called SIMD efficiency. You will actually have nice example exercises in your homework related to this. Your SIMD efficiency is only 1 over 64. Okay, let me continue and finish, and then we're going to take end. So how much does the masking cost in terms of time? When does it become useless because of time use? Okay, that's a very good question that will kind of be answered in this slide. Basically, that depends on how you do the masking. So a simple implementation looks like this. Your vector length is n. You still execute all n operations, but turn off the result write back according to mask. So basically, mask bits become write enable bits into your register file. You're still executing everything in your adder or whatever functional unit, but you set the write enable based on the mask. Clearly, this costs a lot, right? You're wasting a lot of time doing the execution. At the end, you're write disabling the register that you should not be writing to. But this is certainly one simple implementation. This is possible, but it's not energy efficient, and it keeps the function unit very busy. Another implementation is called density time implementation. You can have a function, simple unit that scans the mask vector, because we already know the mask vector, and only selects the elements with non-zero masks. This way, you need to actually do random access to locations in your register file, which hopefully you should be able to do, but not in all cases, right? So basically, this is another implementation, which is actually quite good implementation. This works nicely, of course, if most of your mask bits are 0. If most of your mask bits are 1, then you waste some time figuring out this density time, essentially, figure out which ones. So it really depends. Which works well depends on whether most of your mask bits are zeros or ones. And usually, this one's a better option, though, on the right, because especially if you're operating on sparse vectors, this is a good idea. Here, basically, your functional unit is busy only for those elements you're supposed to be executing on, right? It's not busy for those elements that you're not supposed to be executing on. You figure out by scanning the mask register what you should really be executing on. Okay, I kind of answered which one's better and trade-offs. Clearly, you need to spend some time early on to scan the mask vector over here. You don't need to do that over here. But here, you're executing everything in a vector length. Whereas here, especially if the vector is sparse, you may actually be executing very little. So imagine, for example, a vector length of 64 and a mask register where only one bit is set. Clearly, I would choose the right implementation over here, right? Because I will do only one addition or whatever processing elements computation that I'm doing over here. Okay, so some issues, stride and banking are important, as we discussed. As long as they're relatively prime to each other, and there are enough banks to cover the bank access latency, we can sustain one element per cycle throughput. So this is kind of going to be a review of what we've discussed. So I'm going to go through this relatively quickly, but we've already talked about stride and banking issues clearly, right? And I already said that as long as they're relatively prime to each other and there are enough banks to cover the bank access latency, they can sustain this throughput. So storage format that we also discussed in the beginning very much determines this issue also, basically, whether you can make things relatively prime to each other. Row major, as we discussed, consecutive elements in a row are laid out consecutively in memory. Column major, consecutive elements in a column are laid out consecutively in memory. And you need to change the stride when accessing a row versus column, because you cannot have both formats at the same time for the same matrix. You could, but now you run into a lot of other issues if you do. And I'm already showing you the slide that I showed you earlier, right? Just to jog your memory. If you're doing matrix multiplication of matrix A to matrix B, whenever you're accessing matrix A, you do have a stride of 1. Whenever you're accessing matrix B, you have a stride of 10, as you can see, as we have shown earlier. Now, think about this. If you actually access matrix B, and then you basically multiply matrix B with another matrix X, for example, now you need to access matrix B in a row with a stride of 1, and then matrix X with a stride of whatever, depending on how many columns that matrix has, right? Basically, the point is, depending on your access pattern, your strides could be very, very different. And as a result, it's very difficult, very, very difficult to have a number of memory banks to be relatively prime with your stride. You could choose a memory bank of 16, but then the fact that you're mixing stride of 1 and 10 leads to the fact that you will inevitably get some conflicts in your memory banks. That's why people actually devoted a lot of time into solving the bank conflicts, right? So very quickly, let me cover this, and then we're going to be almost done. But you can watch this lecture, and this is relatively optional also, actually, because we've covered bank conflicts already in this lecture. So basically, you can solve bank conflicts with more banks, of course. If you have 1 million banks, clearly, you will reduce the probability of collision in any single bank, regardless of the stride. But of course, you need to do your data mapping nicely also. Data mapping also is important. That's why number of ports is important, as we have seen earlier. But this is not very feasible, right? Having 1 million banks is probably not feasible, because now your hardware becomes complex. You can have more ports in each bank, as we've done, and as vector machines also do this as well. You can have better data layout to match the access pattern. If you can do that, this is a good idea. And this is exactly what Josh Fisher was discussing. Basically, the programmer needs to be a ninja programmer to figure out how to lay out the data so that you minimize the bank conflicts. Right? Is this always possible? And the answer is no, basically, because you don't always access one data structure with the exact same access pattern. You may access the same data structure with different access patterns. You can do better mapping of addresses to banks, and you should do that if possible. And that's not easy also. Randomized mapping is a good idea, actually. So basically, you don't take consecutive address bits. For example, if you have 16 banks, you need 4 address bits, right? Clearly. You don't take consecutive address bits, but you apply some randomization or hashing to it. And that actually reduces the probability of conflicts. I think I saw some discussion in the chat that talks about prime numbers, for example. And that's another possibility, actually. I didn't see that. Yeah, basically, if you somehow use a prime number to index into your memory, that actually helps as well. And that's somewhat discussed in this RAW paper as well. Okay, so we're almost done. Basically, I will recommend you to take a look at this RAW paper if you're interested. This is a very seminal paper that talks about this. But basically, array versus processor, vector processor distinction is the purest distinction. And most modern SIMD processors are a combination of both, as I said earlier. They exploit data parallelism in both time and space. And GPUs are a prime example we will cover in a bit more detail in the next lecture. Remember, these were the array versus vector processors, but GPUs are actually more like this, basically. Very quickly, this is a vector processor, right? You basically have a one functional unit, and you supply consecutive elements to it. But a GPU or modern SIMD processors look like this. There's some array processing, 4 functional units, and you supply consecutive elements and execute them concurrently. And then you supply the next 4 elements, next 4 elements, next 4 elements, next 4 elements, next 4 elements in the consecutive cycles. So this is a combination of array plus vector processing, as you can see. And this is what a modern GPU kind of looks like. It's actually kind of looks like this. You have vector registers partitioned into these different partitions, And you can supply different elements to these different lanes, if you will. So these are called lanes. You can supply, essentially, you partition your huge register file into some elements that are going to be supplied to these execution units based on what will go into what execution unit in what cycle. So clearly there's a pattern here, right? Elements 0 through 4, 0 through 3 go in the same cycle. 4 through 7 go in the same cycle. 8 through 11 go in the same cycle, but they go in consecutive cycles, which means that by mapping your elements 0, 4, 8, 12, etc. over here, 1, 5, 9, etc. over here, etc. over here, you can basically have a very nice structure, hardware structure, where you can actually do vector plus array execution. Okay, and then that leads to something like this, which we're going to cover at the beginning of next lecture, because I think we're already out of time today. Okay, but I will leave you with this picture, basically. This picture shows essentially what an array plus vector processor executes, just to harp on it, because we've seen it multiple times. But this makes it concrete again. In this example machine, you can have 32 elements per vector and 8 lanes. And basically, each load takes 4 cycles, because 8 elements are executed concurrently in the same cycle, as you can see. So each load takes 4 cycles. Next, you can start the multiply that's dependent. Next, you can start the add. After the load is done, you can start the load again, and then the multiply that's dependent, and then add again. This way, you can actually have multiple function units, as you can see. You can do array processing as well as vector processing over here. This machine is completing 24 operations per cycle while issuing one vector instruction per cycle, as you can see at a given time. Okay, next week, we're going to start with essentially these earlier slides. I'm going to cover them again very quickly to jog your memory. But basically, we're going to see how this is done on a GPU-like machine in a real system. And we're going to see automatic code vectorization as well. And we're going to see also how GPUs can be programmed potentially without automatic code vectorization as well. Until then, I think I will take any burning questions you may have. I think the last question is about masking, which I already answered with that example. But if there are any burning questions, I will take it. Otherwise, have a good weekend. Stay well and safe. And I will see you in the GPU lecture next Thursday. Take care.